And I just wanted to take a minute before we get started to describe what the Northwest Fire Science Consortium is. We are a regional fire science exchange in the Northwest, funded by a national program called the Joint Fire Science Program. And they support 15 of these fire science exchanges across the area and across the US. And Joint Fire Science started this network in 2009 with the objective of increasing awareness, understanding, and use of fire science within ecologically similar regions. And so we are essentially a boundary spanning organization for the Northwest that is trying to increase communication and relationships between managers, scientists, and practitioners about fire and fuels management needs and what science can meet those needs. So again, we cover Washington and Oregon with the exception of the southeast corner of Oregon, which is rangeland. And so that's part of the Great Basin Fire Science Network. If you're a rangeland person, I know a lot of rangelands were affected by fire this year in Oregon. I suggest following the Great Basin Fire Science Exchange as well. So as a regional exchange, we really work to offer different venues for this. Oh, sorry, I should have shown this before. This is our division of the country, and there's our little bump out for the Southeast, which is part of the Great Basin. So if you have fire science questions about any other part of the country, these are a really great place to begin. And Autumn's putting resources and links in the chat. So our personal mission at the Northwest Fire Science Consortium is to accelerate awareness, understanding, application of scientists, and integrate that science so it gets actually applied to fire fuels management. So we hope to use this webinar not only to share knowledge today, but also to hear back from you on what your interests, your needs, and your questions are. And I will add that I should have introduced ourselves a little bit. I am the principal investigator of the Northwest Fire Science Consortium, and I'm also the director of the Extension Fire Program at Oregon State University. My name is EJ Davis. And working with me today and helping put on this webinar is Autumn Ellison. She's the coordinator of the Northwest Fire Science Consortium, and she's making this webinar run smoothly, and she'll answer all your tech questions. She's also a great person to reach out to afterwards if you have questions or needs. We also developed this series in partnership with DNR's Washington Department of Natural Resources Post-Fire Program and with our Northwest Fire Science Consortium partner, because our consortium is a coalition of different universities and organizations, Patrick Schultz from Washington State University Extension. So I'd just like to give some appreciation for them. I'll share just a couple more things about these webinars, and then I will stop talking and turn it over to our presenters. So this webinar and this whole series are intended to create new conversations and new thinking about how we can most effectively recover from wildfire events while addressing resilience and some of the threats to that. So we've asked for each webinar a team of a manager or practitioner and a scientist to share their different perspectives. So what's some of the basic science about this topic and how are managers putting this into use? Today's topic is debris flow after wildfire, because recently burned areas are at risk of flooding and debris flows or rapidly moving landslides. So we've asked our speakers to summarize the science behind why debris flows happen, and then how managers can use that science to mitigate those hazards. I'll note too that we've also asked our presenters, and we ask you too as participants, to consider a trauma-informed approach in how we all engage today, given that we're talking about post-fire. This means we are going to be taking care with the words, images, and tone that we are presenting here. And we're trying to maintain an environment that considers the safety and well-being of everyone here and anyone who may have experienced fire and smoke in any way in their lives. So please help us do your part to maintain this environment by being respectful in your words when you ask questions or provide comments. And also, if you're a fire-affected, smoke-affected person, please feel free to take care of yourself by stepping away or doing what you need to maintain your safety if you would like to do that at any point. And if you'd like to learn more about trauma-informed approaches, OSU Extension has a trauma-informed toolkit, which Autumn will be putting in the box, in the chat box. All right, enough from me. I'm going to turn it over to our speakers. Today, we're going to be hearing first from Dr. Annette Patton, who is an assistant professor and the relatively new forest watershed specialist at Oregon State University in the College of Forestry, so a colleague of mine. And then we're going to hear from Dr. Nancy Calhoun, who is the Post-WildfireDebris Flow Program Manager for Washington Department of Natural Resources, a relatively new program. So Annette, I'm going to stop sharing my screen and you can take it away.
Wonderful. Thank you so much, EJ. I'll go ahead and get my presentation up, hopefully. All right, does that display correctly for everybody?
Looks good.
Awesome. Thank you so much for the introduction, EJ, and thank you for having us here today. It's really exciting to be able to chat with you all about the science and management of post-fire debris flows. As EJ mentioned, my name is Annette Patton. I am relatively new to the role of Watershed Science Extension Specialist at Oregon State University, and I have been researching and studying debris flows of all flavors for quite a while now in various parts of the West, from Colorado to Oregon to Alaska. So what I'm going to do today is start out by presenting just some of the basics of debris flows and what they are. We'll start with a definition of what I mean by the term debris flow. And then we'll also talk a little bit about hill slope responses to fire and some of the processes that might change after a fire. I'll then move into some basic strategies for risk reduction, including a little bit of discussion about one of the tools that you may have heard of or encountered before, which is a model produced by the US Geological Survey. So it's just a little roadmap of where we're going. And as EJ mentioned, this has the potential to be a really serious topic. Landslides and fire have really serious impacts to human safety, infrastructure, livelihoods. So I want to acknowledge any potential impacts that you or people that you know have experienced. I will be showing some photos of things like landslides and burned forests today. And again, if you need to step away and take care of yourself, please feel free to do so. Now, to start, what do we mean when we say the term debris flow? I am a geomorphologist, a geoscientist. When I talk about debris flows, I'm talking about a type of landslide. So that's a rapid movement of material down a hill slope. That could be soil, sediment, loose rocks, or vegetation. And rapid, in the case of a debris flow, can be very rapid because debris flows are a type of landslide characterized by very high water content. So unlike other kinds of landslides, which might move as a somewhat coherent block of material, debris flows, like their name implies, actually flow. I've heard them described as rivers of wet concrete. And if that kind of helps you picture the way that they might move down a hill slope, that can be a useful framework. Debris flows often follow, just like rivers, they often follow existing gullies or stream channels, and topography kind of dictates where they move. And so this is just a really simple schematic showing what they might look like on a hill slope. They tend to start up high on the hill slopes, then move through a narrow channel, and then deposit material when the slope starts to get a little bit shallower. Now, because of that really high water content, they have the potential to travel very long distances, up to several miles, or maybe half a mile to several miles, and potentially at very high velocities. Maybe I think the maximum you might see in debris flow velocity would be 25 to 30 miles per hour. So that's very fast. Also, because if you're picturing a river of wet concrete, they're very erosive. So they're really good at picking up additional material as they move down a hill slope, meaning that they're growing in volume as they travel. And that also contributes to those very long run-out distances. And all of these travel mechanisms result in potentially very high risk to people and infrastructure. And you've maybe heard about some very consequential landslides and fatal landslides in the news cycle, including here in Oregon. There was a fatal landslide in 2021 up on the Columbia River Gorge near Dotson. Or maybe you heard about some of the debris flows that happened in 2018 in Montecito, California. These are both examples of debris flows that occurred in the days or years following a wildfire. And we've talked a lot about water already, and that is also important in influencing when debris flows start. Debris flows are typically initiated by very intense rainfall. And here in the Western US, most debris flows are triggered by a specific type of storm called an atmospheric river. And I want to bring this up because this also might be a term that you've started to hear in the last several years. It's not a new phenomenon, but we do have better tools to describe and characterize atmospheric rivers in the last decade or so. So that word has started to enter the news cycle and various other kinds of media. And an atmospheric river is just a description of a long, narrow band of water vapor transport that brings water from the tropics up to more northern latitudes. And as I said, here in the Western US, atmospheric rivers initiate the majority of debris flows. That doesn't mean that all atmospheric rivers cause debris flows. In fact, most atmospheric rivers bring primarily beneficial and important water resources to the West, but those very severe atmospheric rivers have the potential to cause very intense rainfall and also debris flows and flooding and other hazards. Now, when you get all of that really intense rainfall, there are actually a couple of different mechanisms that might initiate a debris flow. And the first would be a runoff initiated debris flow. And what I mean by that is that water coming, when it comes very intensely, as really intense short bursts of rain, it sometimes can't infiltrate into the soil quickly enough. So it can't absorb into the soil as quickly as the rain is falling. And if that happens, you can start to see erosion. Things like little tiny channels or rills will develop and then coalesce as you move down the hill slope. And so this schematic on the left kind of shows you what that might look like if you have so much water coming from the sky that can't get into the soil quickly enough. You might have dry soil at depth, but there's a lot of water flowing over the surface of the hill slope. And when that water coalesces, that's when you'll start to see a really concentrated surface water flow that might have the ability to pick up a lot of sediment. And so a lot of water, a lot of sediment that can then transform into a debris flow. Some of the factors that influence whether or not a debris flow initiates, if there's a lot of water and this runoff forming, are things like how quickly can water infiltrate, how quickly is the rain falling, and what's the availability of fine sediment or soil to be eroded. So is there even material that can be moved by this surface water runoff? Another common mechanism of debris flow initiation are shallow landslides. So again, this is kind of thinking about categories of landslides, but here I'm talking about landslides that might initiate as a more coherent block of material that slides along some plane, some planar feature in the hill slope. Not often, but not always happens near the base of the rooting zone. So there could be other layers that matter, that root strength might matter, but if you get enough water saturating the whole soil column, you reduce strength of the soil or sediment by adding all of that water. And then you might just see that slip or kind of coherent movement of material near the top of a debris flow. And then because there's so much water involved, it can then fluidize and transform into that river of concrete that we call a debris flow. Now, this is common, maybe in the first meter to several meters of depth of soil or sediment on a hill slope. And some of the factors that influence this type of initiation include things like how strong and cohesive is the soil? Are there a lot of roots that are adding additional strength and cohesion? Or it might also relate to things like how is shallow groundwater moving through the soil? Can it move laterally, side to side in the soil? Or are there layers that are preventing it from going deeper into the soil? And of course, the depth of the soil matters here too. You need enough material to kind of have mass that becomes a landslide failure. So that's all descriptions of sort of general processes that influence debris flow initiation, and that can happen in any steep hill slope setting. So today we want to talk specifically about fire. So I want to take a few minutes to talk about how fire might impact forested hill slopes. And I'll talk some about some of the processes of fire, but also how that might apply here in the Pacific Northwest. Because to give you a little bit of a spoiler, a lot of what we know about post-fire debris flows comes from Southern California and more arid places in the interior West. So there's some questions and ongoing research about how these processes might play out here in Oregon, Washington, and Northern California. Now, the first thing to think about is what happens immediately after a fire. How do fires transform hill slopes? And one of the big changes that happens right away is changes to those runoff related processes. So how water might start to accumulate and flow along the surface. One of the processes you've maybe heard about before is that after a fire, when you burn a lot of vegetation, you might see the development of a water repellent layer at the top of the soil. That could be a couple of millimeters up to maybe a couple of centimeters thick. And that water repellent layer prevents water from getting into the deeper soil. You might also hear that described as a hydrophobic soil. Another important change is that fire can result in a very smooth hill slope surface. So if you think about a forest here in the Pacific Northwest, you might think about ferns, downed logs, a lot of material and low-lying vegetation that creates a very rough surface. Instead, after a fire, you often will see really smooth hill slopes like the photo on the right there. That's from the Holiday Farm fire here in Oregon. And when you have a really smooth surface, it's really easy for water to start flowing across it. There's nothing holding it back. And then, of course, as you lose all of that vegetation, you're no longer preventing rainfall from hitting the ground. Vegetation is really good at intercepting raindrops and preventing them from directly impacting the soil. And then, of course, the vegetation loss means that you've reduced transpiration. So vegetation is really good at pumping water out of the soil and back into the air. And after vegetation dies, you lose that ability and you might have more water accumulating in the soil. So all of that can start to happen and start to influence runoff processes very quickly. These are some examples of what that runoff might look like, or some evidence of what runoff might look like. So you can see some of those little erosional features or rills and movement of duff or fine sediment along the hill slope. Now, there are also some longer term changes. That change in transpiration rate, of course, is very important, but you also might see that after a disturbance like a fire, all of the tree roots that previously were really good at holding the soil together will start to decay, and that takes a little bit of time. So over the maybe 2 to 10 years following a fire, you might see a decay in root strength that was previously helping hold all of those soils together. And these plots show some examples from a couple of sites here in the Oregon Coast Range. And what is now outlined in red, those lines showing lateral root strength, that's describing how the strength from roots is declining after a fire. So in the sort of 2 to 10 years after a fire, you see a really rapid drop in root strength as all of those fine roots and then some of the bigger roots decay in the soil. At the same time, after a fire, you'll start to see regrowth. So as new vegetation comes back in, you'll see new development of roots, and you'll start to regain strength in the maybe 3 to 10 years following a fire. And whether or not that returns to the original strength of the pre-fire forest depends a little bit on what grows back. Are you going back to trees like conifers and hardwoods, or are you seeing a recovery of primarily understory vegetation? So you might have a new total strength value from those roots. And either way, there's going to be a dip where you have the minimum amount of root strength, where you've got a lot of decay and not a whole lot of new growth has come back in. And on these plots, those little yellow stars shows examples of landslides that occurred at these 2 sites in the Oregon Coast Range when there was a very low total root strength in the soil. So that happened in these cases 8 to 10 years after the fire. Now, if you think about these 2 different processes, part of why I've spent so much time talking about them is because you might then expect to see a variable susceptibility in these different processes at different timelines after a fire. So those runoff initiated debris flows are most likely to occur in the first maybe 2 years after a fire, when you have that really hydrophobic layer, or that water repellent layer, and not a whole lot of understory vegetation has grown back. And in contrast, you might see the greatest susceptibility to debris flows triggered by shallow landslides in the maybe 3 to 10 years following a fire. Now, I've dashed these lines here because this is sort of a hypothesis. We don't know everything about the exact timelines and how that might vary from place to place, even here in the Pacific Northwest. So those exact timelines are subjects of ongoing research, as well as questions about whether or not there's going to be a return to baseline strength and susceptibility and what timeline that might look like. Because again, that might vary from place to place. Another active area of ongoing research is how this might play out a little bit differently here in the Pacific Northwest. We're starting to see, of course, more and more severe fires impacting large areas of forested mountains. But a lot of what we know comes from Southern California, New Mexico, and the interior West with very different climates. So here in the Pacific Northwest, of course, there are some differences that might really matter for how these processes play out. We have much higher rainfall, particularly west of the Cascades. We have very dense forests out here. You might also see really variable soil depth. There are some parts of our mountains that have very thin, rocky soils, and other places with more gentle hill slopes that have much deeper soils and more sediment available for debris flows and other landslide processes. Another observation that we've seen from this region, Oregon and Washington, is possibly that hydrophobic layer being very patchy. Jackson and Roaring have a study that observes places where hydrophobicity does occur. So you do have that water repellent layer, but there are places still where water can infiltrate in the soil. And the photo on the right is illustrating what that looks like a little bit, where those really light colored areas are dry soil. So you see a lot of light reflecting back into the camera. But to the left and right are very dark places where water has infiltrated into the soil. And all of this might mean that we have different susceptibility to increased runoff and different susceptibility to those runoff versus shallow landslide initiated debris flows. And that leads to this ongoing question about what the primary mechanism for debris flow initiation is after fire here in the Pacific Northwest. And again, that matters because the timelines for when we would expect to see landslides and the type of storms that might initiate them might vary depending on which process we're more susceptible to. Now, we've talked a lot about how landslides and specifically debris flows initiate. I want to talk a little bit about some strategies for risk reduction. And I could talk about all of these ideas listed here for hours each, because there's a lot of ways to think about reducing risk from landslides like debris flows. And here on this slide, I've organized them sort of along timelines of how much advance warning you have to prepare. So on the top, maybe you have a lot of time to think about preparation, maybe even in advance of a fire, would be things like mapping out potential hazards, implementing structural mitigation. So those would be things like barriers or debris retention basins. And then as you get closer and closer and maybe are moving more towards the response and recovery side of things, there's a lot you can still think about in terms of education and early warning, maybe using models to predict which storms are likely to trigger landslides, and then using that as ways to inform evacuations, for example. And of course, it's important to consider those response and recovery operations as well. Coordinated response and recovery, like for any hazard, are really important for mitigating risk to communities. Now, one of the models that I wanted to spend just a little bit of time thinking about is the model developed by the US Geological Survey for post-fire debris flows. And I wanted to talk about this one for at least a couple minutes because this is something that you might see in action as a practitioner or in risk conversations. And it's very commonly used by a lot of state and federal agencies. And the US Geological Survey has developed this model and provides assessments of post-fire debris flow susceptibility, I believe, for any state, federal, or even local agencies, depending on their capacity. So if you want to know more, I put a link here on this slide, and I think Autumn's going to put that in the chat as well for more information. And so I wanted to talk about what this model is and what it's doing. This map on the left is showing an example of a post-fire debris flow assessment for the Archie Creek fire here in Oregon. And you can see that there's a lot of bright colors, reds and oranges. And essentially what they're modeling here is estimates of debris flow probability and volume. They use a statistical model with inputs that include things like basin topography, how much of the upslope area is very steep. In this model, they use a cutoff of 23 degrees slope angle. They also input things like burn severity and soil properties that relate to those infiltration characteristics. And all of this is in response in the model to a design storm, where they, in most cases, the USGS assessors are assuming a 24 millimeter per hour storm for at least 15 minutes, which just means that it's a very short duration of intense rainfall. And this is all intended to describe primarily those runoff-induced debris flows. And that's relevant because I also want to just take a moment to think about some of the best applications and limitations of this kind of model. It's intended to capture these really watershed scale controls in a very rapid assessment. And it uses national data sets so that you can sort of run these models really quickly and estimate relative susceptibility to debris flows at a watershed scale. So if you think back to that map of the Archie Creek file, you saw a lot of sort of tributary watersheds had different colors. So most of these are thinking about watershed scale susceptibility. And that means it's really useful for immediate response, maybe some triage of response and recovery. And it's good about thinking about relative susceptibility and maybe places to continue to focus further risk reduction efforts. There are some limitations to appropriate use of the model. For example, it was built primarily using data from Southern California and then tested in primarily the interior West. This map shows some of the sites where they've collected data to build the model. And you'll notice that there's a big hole in Washington, Oregon, and Northern California. And it's again intended to describe primarily these runoff-induced debris flows. So the US Geological Survey and their collaborators are currently working to validate and calibrate this model for use in Oregon and Washington so that it can be more accurate for this area. It's still a really useful tool for relative susceptibility. It's also intended to be a snapshot that describes primarily runoff-induced debris flows immediately after a fire. So it's not intended to capture how that susceptibility might change through time in the years following a fire. And lastly, it's not intended to be site-specific. So again, it's thinking primarily about these watershed scale controls, and it's not an individual site assessment. Now I'm going to wrap up here because this is a really useful tool that is one of the tools that might be useful for practitioners in thinking about risk reduction. There are many others, but for that, I think I'm going to hand it over to Nancy.
Thanks, Annette. I always learn something new when I talk to you. It's great. Gonna share my screen. All right. Would someone mind verbally acknowledging they can see my screen, my presentation?
We can't see it, Nancy.
You cannot?
No, I can't see. We don't see anything.
Thank you. First, oh, there it is. How about now?
Now we do. We see it in not presentation mode. We see all the slides on the side.
How about now?
Perfect.
Okay, great. All right. Thank you, Annette. So now our next question is, how do we use all this science that Annette has just really clearly laid out to reduce our risk from post-fire debris flows? Today, I'm going to focus on how the state of Washington is taking on this challenge. I'm Nancy Calhoun. I'm new to the Washington Geological Survey, and that is a division within the Department of Natural Resources, or DNR, as I'll refer to it today. The survey's vision is to make a safer, more productive, and resilient society by using geology in regular thought and decision-making. In the state of Washington has had its share of wildfires, as well as landslide disasters. In 2023, the state legislature passed the Cascading Impacts After Wildfire Act with unanimous support. The new post-wildfire debris flow program at WGS is a tiny part of this broader act. We're a growing program. I'm the first full-time member, and we're recruiting for 2 more team members now. So this is a growing program, as well as sort of a cutting-edge area of scientific research that Annette has so nicely conveyed. In this act, these bullet points are pulled out of this language direct from the RCW. So the program is to identify areas that may experience post-wildfire debris flows, assess burned areas, improve our modeling to understand debris flow triggers, which will hopefully lead to early warning for communities, and communicate all of this with emergency managers, local governments, partners, the public, and interested parties. So I'll walk through how we at the WGS are currently approaching these different aspects of the post-wildfire debris flow hazard. And I'll start with our post-fire assessments. Our team is named the Wildfire Associated Landslide Emergency Response Team, or WALERT, which is for short and what I'll be saying today. When a fire is winding down, rule of thumb, about 80% contained, and we're in communication with the incident command, we'll go out and assess things on the ground. Currently, there are several members in the landslide hazard program at WGS who have their red cards and have been trained on ground truthing soil burn severity maps, which are critical pieces that feed into the USGS debris flow model that Annette discussed and are used for different land management, decision-making and mitigation efforts. So as I said, geologists at WGS have been doing this for a while, and you may have heard of Kate Mickelson, who is the landslide hazard program lead. And so they have been doing this work throughout the state of Washington. Here's a map, and the red blobs are fire perimeters that we have assessed with the Wallert team in the past slightly longer, 7 years. Today, I'm going to focus in on the Pioneer Fire in north central Washington, which is along the shores of Lake Chelan. On the left, we have the soil burn severity map. This is something that the U.S. Forest Service Burn Area Emergency Response, or BEAR teams, often make based on satellite data that was remotely sensed, and then they go out and ground truth it. This is a key piece of what ends up being the combined hazard USGS debris flow model that Annette presented. So we use the combined hazard. The USGS debris flow model has a lot of different iterations at different design storm levels, just looking at stream segments and volume, likelihood, probability of debris flow. However, the limitations that Annette described on where this data set for the debris flow model was made means we mostly use the combined hazard model. Sort of as a rule of thumb, could a debris flow occur in any given burned basin? And if so, what's the general likelihood of that happening? We take this data and focus in on life safety and property in a given burn area, regardless of land ownership. The Wallert priorities are identifying houses, other structures, and things like roads or utilities that are exposed to debris flow hazards. We first map in the office using LiDAR and remote sensing. LiDAR is high-resolution topography data that you see in the background of this map on the right. And we look through air photos to see if any debris flows have happened before the fire, which can tell you if it's a debris flow prone area already, which fires then exacerbate that likelihood. Then we visit as many of these locations as we can in the field. This is a rapid response effort, and we aim to publish our report within a few weeks of returning from the field. We follow up with interested parties and support emergency managers, conservation districts, or other folks who are then responsive at the local level, both to generating public awareness of this hazard and responding during post-fire recovery. So awareness that this hazard exists is our primary defense, and knowing where the risk is also helps communities plan mitigation efforts, whether that's hard mitigation, like the debris flow dam Annette showed from Italy in one of her slides, or increasing communication tools locally. Now I'll get into our post-fire monitoring. As Annette described, the USGS model is built on past debris flow events from Southern California and the Intermountain West. And we have different climate, ecosystem, weather systems, and geology in Washington. And it's diverse within the state. This applies to Oregon and the rest of the Pacific Northwest as well. So we are actively adding to this data set to make the model more accurate for Washington. And I know that Bill Burns from the Oregon Department of Geology, or DOGAMI, is also making headway on this front in Oregon. Most of our post-fire monitoring is geared toward this goal, and we are working closely with the folks at USGS to improve the model, which is so helpful for us all. So with that improved model, we will have a better sense of which rainstorms can trigger debris flows. This is one of the best forms of early warning we can hope for knowing which rain events are likely to cause debris flows. And a quick shout out, Annette did a great job describing atmospheric rivers. And on the east side of Washington, it's sometimes our convective thunderstorms that are more summertime storms that can trigger debris flows. So it's different for different parts of the Pacific Northwest as well. Here's our website and a map of fires where we have equipment and post-fire debris flow observations. You can, I'm going to zoom in on this black box. You can see the fuzzy dots are post-wildfire hazard events that have occurred and their approximate locations. You can also go look at our telemetered weather stations that are deployed out there and see live weather data. And this is called our post-wildfire debris flow dashboard. We're adding other post-fire monitoring data like using game cameras to capture the exact timing of a debris flow. This GIF is from the 2021 Cedar Creek burn area from a July 2023 debris flow event. We then align our timing that we capture with the game camera with our weather observations, hopefully at the 15-minute or finer resolution, 5-minute is great, so that we can get what rainfall event actually caused that debris flow. So with enough of these paired observations, we can get closer to useful and accurate rainfall thresholds for debris flow initiation. These maps are from the same fan as that last slide of that GIF of the debris flow. We also gather detailed volume estimates after a debris flow occurs, and these observations will add into the model what magnitude or how much mass or how big of a debris flow we can expect. So the fan, debris flow fan is approximated in the black outline, and then actually a local resident created the map on the left, and this is our direct field data in red and purple. And the purple is the debris flow shown from the previous slide. There was another debris flow on this fan in August of this summer. Next, I'll get into what we can do a more proactive approach, which is mapping alluvial fans before a fire occurs. This identifies potential hazard areas and also starts the communication and awareness building at the local level that these fans, and if a place were to burn over, then there might be a hazard. We have a current grant-funded project that is in north central Washington in these 4 counties. The study area is the purple, which is a very funny looking study area. However, on the right map, you can see all those little black dots are houses and lifelines in red that connect these communities, or roads and utilities. So we concentrated our mapping areas where people are located. So where the hazard intersects with the people and their infrastructure is where the risk is. We've been working with these counties throughout this project so they can be prepared for the data that will come, and also start thinking about how to use this data in proactive ways via mitigation ideas or other communication efforts. So I've brought up awareness several times. Knowing that a house or your fire station is located in a place that could experience debris flows after fires, then lets people make a plan and decide what to do themselves. This is one of our pamphlets that we hand out when we go out in the field or give to local emergency managers or other communicators in the public. Some of our primary takeaways are for awareness building are to sign up for the National Weather Service alerts. As Annette clearly explained, it's often rainfall that triggers these debris flows. And so when a really intense atmospheric river or an intense convective thunderstorm is coming, the National Weather Service can send alerts, and that might be our best form of early awareness or early warning. Also, knowing your own personal situational awareness. Have debris flows happened in your area before? Are you located on a fan? Knowing this before a fire can just start the decision-making process and build awareness. And it's usually a good idea, but in particular for community resilience, talking with your neighbors, sharing what we know, what we've observed in our neighborhood, it can be so valuable. So back to our Cascading Impacts After Wildfire Act. We've now seen how we are mapping areas before fires, assessing post-fire debris flow hazard right after a fire with our WALERT team, and where this new post-fire debris flow program is growing and hoping to use science and our own building scientific observations towards improving our debris flow model, hopefully leading to early warning for communicators. And communication, it's an ongoing and equally critical aspect of this work. I want to acknowledge that to do any of this work takes solid partnerships. This is just a selection of folks with whom we work. We also work with other divisions within DNR. Local conservation districts are an awesome resource, emergency management departments, and other local decision makers and champions. If we don't work together, it is much harder to get anything done, and we can get, so I would like to encourage us to continue to collaborate. And with that, I want to thank the Northwest Fire Science Consortium for this webinar series, and thank you all for your attention.
Thank you so much, Nancy and Annette. Those were great presentations. A lot of good information was shared, and it was shared in, I thought, a really clear way as someone who's not an expert on debris flows. So we appreciate that. Autumn has just put a link in the chat asking you if you need to leave early, please just take a minute to take our survey at the link that she's provided there. It honestly will just take about 1 to 2 minutes, and the feedback is really valuable for us. So we're going to move on to Q&A for the remainder of the time. And so please go ahead and put your questions in the Q&A box. That is where we are going to be taking questions. And I'll let Nancy and Annette decide how they'd like to respond to those. So it looks like we have one there. I'll read it aloud. What weather and precipitation forecasts do you use for early warning, particularly the 15-minute rainfall intensity? You can decide who wants to take that.
That I can say that the different regions of National Weather Service have taken this on in part. They are the most familiar with what rainfall to expect, and they are also already geared for communicating warnings. So folks are already sort of integrated with National Weather Service, so they are the best ones. However, our observations from that pairing of when a debris flow occurs and our finest scale resolution rainfall observations, that's really what we are trying to get now and build that data set. Let me see if that answered the question. Oh, and I can also say that the USGS debris flow emergency assessment, hazard assessment, has a variety of rainfall intensities that you can look at. Because the Pacific Northwest differs so greatly than their training data set, we often use their 24 millimeter per hour rainfall rate as our default if we do not have any regionally specific data. So I hope that answers your question.
Yes, and while you're talking, Nancy, we had another question. Is that September 2024 DNR report available online?
Sure is. If you are talking about the Pioneer Fire, then yes. But all of our WALERT reports from this year, we've published 3 so far for the Easy Fire, Pioneer, and Retreat Fire. I can hopefully get a link.
Great, go ahead and put a link in the chat whenever you can. Annette and Nancy, I'll leave it to you. We might not be able to get to all the questions, so take a look at some of the questions that are there and see which ones you'd like to answer. Maybe there's one that Annette would like to answer.
Sure. Yeah, there's some really good questions in here, and I hope we have time to get to all of them, but we'll see what we can do. I see the top question here is about how debris flow characteristics vary between wildfires and prescribed fires. I like this question a lot because it gets at some really important differences between how different fires play out. And that could be wildfire versus prescribed, or even just different burn severities. One of the really important predictors of post-fire debris flows is just simply burn severity. The more severe the burn, the more you've lost vegetation, the maybe larger the impacts to that soil water repellency and things like that. So in general, the most severe fires tend to also have the most severe impacts from debris flows. Nancy, is there anything you'd want to add to that? I don't know of a whole lot of direct comparisons, though, that specifically look at prescribed versus wildfires.
I'll take a straightforward question from that, well, that I have an answer for, from Joe Blanchard about the question is, does your post-fire debris flow monitoring include much on the west side of the state of Washington? We are monitoring the Bolt Creek fire. That's outside of Seattle, and Washington hasn't had many west side fires recently. We are very interested in monitoring those that do occur, and I know that Oregon is monitoring several of their west side fires.
Great, thank you. Annette, maybe you'd like to choose from the questions that we have
Sure.
now, one that you feel is good for you.
It's like going to a candy shop and trying to pick the best candy. They're all really good questions. I see one here that's asking about innovations that could help with responding to and mitigating risk. And I think this is a really important topic to maybe spend another minute on too. There are so many innovations that are in progress now and that are, being developed in partnership with researchers and practitioners. One of the topics that Nancy mentioned is just doing a better job of understanding which storms are likely to contribute to debris flow initiation at all. So, that comes down to a lot of data availability questions, trying to collect data with really high resolution, both like high resolution temporal rainfall data, getting really good inventories of where debris flows are happening, and kind of connecting those records as best we can to improve our understanding of which storms trigger debris flows. That's a really big question that also varies regionally. And again, it varies depending on what process you're talking about, what landscape you're talking about. So there's a lot of nuance to that question. Some of the work that I've done in Alaska also links not post-fire specific, but debris flows in general to slightly longer timescales of rainfall than other places. So maybe more like the 3-hour intense rainfall, or, lots of different time scales that matter. But of course, that is just one piece of risk reduction. There are ongoing innovations about really effective tools for detecting landslides and debris flows when they happen. So various monitoring tools that use GPS or sound or seismic vibrations to detect when an event happens, which again contributes to those inventories, but also potentially could provide a couple of minutes warning, which may or may not be useful. And then our engineering collaborators and colleagues are always looking for effective ways to develop structural strategies as well. And that doesn't even get into the social risk reduction efforts of education and community planning and resilience and things like that. So a million innovations. Let's keep going.
That's a great topic. Nancy, I'll just note there's one question in the chat and then one question in the Q&A, and I think you could answer them together. So the questions are, reminding us of what was the name of the post-fire, the WALERT team. Is it similar to the California WERT team? Is it associated with USGS? And then in the chat, can you explain in more detail on a broad timeline how the WALERT team collaborates and integrates with the BEAR team to come up with the post-fire assessments, post-burn assessments?
CJ. The first one, yes, we are similar to the WERT team, which is a California team. They have a slightly, if I don't know the entirety of how they are structured, but they have a slightly different purpose and purview. But we have learned quite a bit from the California Geological Survey, who have been working on this hazard and been working on landslides generally for a while. So WALERT is not affiliated with the USGS. However, we collaborate closely. So we take as much data as we can collect, and we give that directly to the USGS, and they are helping us directly also. So it's quite a close collaboration, but we are not fully related. And then the second question was how we integrate with BEAR, the Burn Area Emergency Response with the U.S. Forest Service. Is that right? Yeah. Okay. We have gone out as the geologists on a BEAR team as state partners. So we have been in the field with them. They write their own report and we will write our own report. But that is also where we received some of the soil burn severity ground truthing training. So that has been a wonderful collaboration. But we're not always integrated like that.
Great, thank you, Nancy. We're going to take a couple more questions, but I know people are starting to drop off, so I'm going to remind you again that if you are leaving, please help us out by clicking on this link, helping us understand your impression of this event and your needs and interests for future events. Nancy and Annette, I'll leave it to you to look at the remaining questions and see which ones you might be able to address. I think we have time for probably one or two more.
I see there's a couple of questions here about current or planned research about salvage logging, replanting, mature versus younger forests. I think these are also all really good questions and good ideas if they're not ongoing and active research projects. I know that there are a number of entities around the Pacific Northwest who are thinking about a lot of these questions. Nancy, I don't know if your team is looking directly at any of these, but I think what's maybe a general answer is that a lot of what we know about fire response, there aren't that many folks who are, the Washington Geologic Survey, the Oregon Geologic Survey, the US Geologic Survey, some of our Forest Service colleagues. There aren't that many folks that have until fairly recently starting to really dive into these connections between forest practices and specifically post-fire debris flows. So all of these are really important topics and areas that could be developed. There might be folks who are looking into some of these questions that I'm not aware of, but I think this is just in general a really active area of ongoing research, lots of questions to ask. So keep asking these questions.
Nancy, do you see any questions you'd like to answer and get the last word on? This will be our last question.
Sure. Patrick Haggerty's question in the chat about whether or not these pre-fire alluvial fan mapping efforts in Washington are intended to inform land use planning efforts. They absolutely are. We make the data, we map to the best of our abilities, we communicate what those maps mean, and then it's up to the planners and others at the local level to decide how they want to use that data. So I just wanted to clarify that, but I think land use is a great usage of these hazard maps to reduce risk as the goal.
Great. Well, thank you both so much. I'm going to just put another link in the chat reminding you that if you registered for this webinar, you will be getting a link to the recording, which will be posted on our YouTube channel within a few days. You can also access these on our webpage. And if you haven't already, I suggest checking out our webpage and signing up for our newsletter. We have a lot of resources. Maybe Autumn, you want to pop the newsletter registration link in the chat. Autumn puts out this newsletter pretty much monthly, and it's just full of so much good information. Annette and Nancy, we're really grateful for your knowledge, your input, and everything you shared with our group today. It was really well done. So as you sign off, a link is going to pop up that is going to ask you to take the survey, or you can grab it in the chat right then. With that, everyone have a wonderful day, and thank you again for joining the Northwest Fire Science Consortium in Washington DNR today.
Thank you, EJ.
Thank you all.
And thank you, Autumn.